Good afternoon, everybody, and let me. I uh, yeah. So we are here for the for our talk on it's like the versatile supermaterial, and it's today the speaker is Dr. Dinuka Gallaba. And let me elaborate on IPSL, Institute of Physics Sri Lanka. Um, the Institute of Physics, IPSL, we say, is a professional body which was established in way back in 1980, incorporated by the Parliamentary Act number 12 of 1986. So the IPSL is the apex body of all physicists in Sri Lanka, and we work for a common goal in order to develop physics in and its applications to upgrade the quality of people. So our main objective is to promote and advance the science of physics and its applications in Sri Lanka through the implementation of diverse activities and projects. So the institute represents all the physicists and all the who works for in many branches in physics. I will not take any time, and I will call upon Dr. Chaturani Upiarachi in order to introduce the today's speaker. Chaturi?
Yes, thank you so much, sir. And it's my pleasure to welcome our resource person, Professor Dinuka H. Gallaba. Currently, he is a visiting assistant professor at Boston College, Massachusetts, USA. He has acquired his Bachelor's of Science, specializing physics back in 2010 from University of Sri Jagadhanapura, and he did his Master's in Physics 2015 from Southern Illinois University, and PhD is also from the same university back in 2020. And his primary research work is carried out in the field of adsorption mechanism of materials and device applications, applications in energy and environment, chemical engineering, petroleum engineering, and device physics. Without much further ado, this digital platform is yours, Professor Dinuka.
Thank you, Dr. Satri. I'd also like to thank you, Professor Shanta Gamage, who invited me for this seminar series. And it has been great honor and privilege to take part in this IPSL seminar series. And I can see some familiar faces that, back in my bachelor's degree, and also people who have inspired me to take on physics into my further studies. Without taking any time, I will like to start my presentation. So let me share my screen. Okay, I hope everybody can see my screen. Just let me know if if you don't see it. Anyway, as a seminar series, this has been a great so far, and I would like to actually start by bit of introduction to my research and some of the work that I did in my PhD. I actually worked on materials that are more relevant to chemical engineering applications, even though I was an applied physicist. These materials have been introduced to the field of chemistry and chemical engineering in recent years. Has been really a boost in material science. So this field basically kind of dominated by chemists and chemical engineers. And we are kind of a very few groups that are working on this field as a material characterization part of this field. But mainly this is basically governed by most of the petroleum and energy industries. So my kind of the main topic of today's talk is about a material called ZIF-8. If I break it into part, it's zeolitic imidaclylate framework 8. It's a mouthful of word, but we'll call it ZIF-8. And I just want to introduce that relatively new material to the field of physics in Sri Lanka. So let me start, and just a slight outline or plan for my today's talk is I want to introduce the techniques and characterization techniques that we've been using to investigate these materials, and a bit of introduction about what these ZIFs are, mainly are, and what kind of a material class that they belong to, and some of the projects that we have conducted on these materials back in my PhD research. And at the end, I'll summarize and show you some of the applications that are kind of give the name ZIF-8 as a versatile material. Okay, about the motivation for my work is where why is the absorption? Absorption, the first thing that comes to your mind is the absorption. It's not AB, it's adsorption. It's basically a physical interaction between a material and a gas or a liquid molecule. So adsorption is taken as a backbone mechanism of many energy and environment applications. And it's an integral part of material discovery and characterization. And the material that we are concentrating on today belongs to a class of materials called metal organic frameworks. There have been over 20,000 functional materials that was discovered or synthesized in this class, and they're really versatile and tunable, especially the materials, the metals and organic parts that are kind of set up as a building block materials for many applications, such as gas storage, carbon capture or CO2 capture, and chemical sensors, and also in most of the solid state electronics devices. So a bit of background about adsorption. What is actually the mechanism of adsorption? It's basically, before we move on to the adsorption, we need to just kind of glimpse through how the gas molecules, or basically most part of the adsorption research are carried out in the gas region. So you might have you already know that energy distribution of gas molecules are having a Maxwell-Boltzmann distribution, which is depending on their velocities. So it has a bell-shaped curve. And when we introduced a material into the system, what happened is that there is a certain potential that keeps these gas molecules bound to its surface. And this interaction is not a chemical interaction. It's all depends on Lennard-Jones potentials and electrostatic potentials between the two molecules. So especially in the computer simulations, we can see this kind of surface on top of the material that can trap these gas molecules just hovering above its surface. So this mechanism is a reversible mechanism, so that when you stick certain amount of molecules on a surface and given a certain energy, you can always take them back or reverse the whole process without harming or without changing the state of the adsorbent or the gas molecule. So this is a good way of storing gases and trapping carbon dioxide, especially because that we can recover them back at any time, any given time, by using a very little amount of energy. So there have been so many research going on since 80s or even 60s about adsorption, especially experimentally. It is basically a combination of statistical physics and thermodynamics. Even though this, the material-wise, this field was mainly dominated by chemistry, the characterization part or the adsorption part is basically the statistical physics theories and thermodynamics. So, and again, a bit of a background about gas adsorption particularly. As I said, the adsorption happens in a very low energy levels. We call physisorption, which is about even less than 1 electron volt of binding energy between the two molecules. There's another part of adsorption called chemisorption, where a chemical bond is taken place. So that process cannot be recovered. So we are looking at the physical adsorption part or physisorption part of this mechanism. So here, actually, this is what we call a 12-6 potential or Lennard-Jones potential, which has been a kind of a backbone of adsorption. And this is the potential that traps the gas molecules on the surface of those materials. So as in a graph, I can show you that the minimum energy or the minimum state of energy to trap these molecules at this point where your London dispersion forces and the polar repulsion forces are kind of balanced out. And this is not an electrostatic force. It is basically a combination of a repulsion from poly repulsion and London's dispersion forces. So if you take two molecules at once, and one of the molecules actually induced a dipole on the other because of this cloud of electrons around it, and make it kind of hovering around the substrate, so that it is trapped, but physically not, it's not chemically, but physically trapped on that potential. So this is just a simple model, but we have a, this is actually a simulation for one of my systems that was done with Monte Carlo simulation. This is a 50 frame video that was actually created from actual data. So you can see that the material that I was talking about is this big cage-like structure. And this pink color molecules are xenon atoms, and they are basically kind of hovering around and vibrate. And this simulation was actually done with the real-time data. So the surface that we call the Lennard-Jones maps or potential surface depends on the gas that is interacting with the molecule. So this ZIF8 molecule or ZIF8 unit cell has a physical size like this with van der Waals size simulation molecule. And you can see the three surfaces that actually come out from calculations of heat interaction with helium. You can see an adsorption surface, and the nitrogen has a bit of different absorption surface because the size difference and the interaction energy difference. And the xenon is a much bigger molecule or an atom that interacts with the ZIF8 and have a surface or adsorption surface like that. It all depends on the size and the interaction energy between the two, the molecule and the substrate. So that's a bit of background about adsorption, but let me move on with the main material that we're concentrating on. It belongs to a metal organic framework class, It's an artificially made material that has been, here for last couple of years, maybe last 20 years, because it has been a really flexible, or I would say it can be tailored into many different applications by just changing the metal cluster and the organic linker. You can change the size or the surface area of the material, and it can be easily tailored to a particular applications. So mainly the MOFs are the metal part or metal cluster that belongs to the MOF are mainly taken from the transition metals or in the part of the S group. And the organic linker, of course, contains carbon and a couple of others classes of elements on this periodic table. And a bit of history about the metal organic frameworks. It has been here for a long time as a different name. They start with what we call the chemical coordination chemistry or coordination polymers. And then it was, first basically started around 1950s, late 1950s as porous coordination polymers. And then at around 1995, Professor Omar Yagi, who was a researcher at the University of California, Berkeley, was actually called, he was kind of named as a father of the metal organic framework. He was a chemist. He was the one that started this metal organic frameworks and start synthesizing the materials that can be actually tailored into a particular application. So then after that, there have been so many investigations and synthesizing a class of materials in both in experimentally and also as in a computer simulation materials. So this field had started to boom in early 2000s, where the people have started there being emerging materials in many different places in the world. For example, the ZIF, the ZIF-8, the material that I was actually going to talk about today, started very recently in 2006, where a subclass of metal organic framework started to kind of emerge. So this subclass is a very kind of a versatile, as I said. It's very applicable in many different cases. As you can see that you can have many combinations of metals and organic linkers to make up these type of material. All these materials are artificially made. Of course, some of them are a bit poisonous to work with, but many of them are not. They're highly stable in water and also highly stable in temperature. And then after that, people start to work with many different types of materials, and people start to making some record-breaking discoveries where this effective surface area of this material was the key, or the star quality of this material, which we can see here. Some of the like very high surface area materials was discovered in 2012 in Northwestern University, which has a 7,000 meters squared per gram. So it's an effective surface area. It's not like a nominal surface area. It's where the materials can, or the gases can interact with the material more if you have more effective area. So the most recent discovery was actually done in Germany, which was having the highest known effective surface area for these type of material. So this has been has been here for a really long time, but in recent years it has picked up some speed, and you can see the number of publications has kind of increased exponentially in recent years. And also you can see here the Cambridge structural database. Out of the total material, the MOFs has been increasingly have the highest rate of number of materials that are entered into the Cambridge structure database. So that's a bit of a history about metal organic frameworks. And this is basically, you know, some of them that you can see as a, structures that we can find. The ZIFs are having a different shape, but it's mainly belongs to the same class of material. So what makes these MOFs unique is mainly it's the flexibility of the structure or flexibility of the applications. And there have been so many materials made in a lab as a prototype, and also there have been so many materials that are actually used in industry these days. Especially these are some of the companies that are kind of known to use these MOFs or make these MOFs as an industrial applications for water harvesting, carbon capture, storage applications like methane and hydrogen, because I've seen that recently in Sri Lanka there was a quite talk about these gas storing ways of storing gases, and MOFs can be actually used to store gases in a very low pressures. So that's another application that is the MOFs has been using for a while. So MOFs kind of stands in between the micropore and mesopore structures. Like the activated carbon, it's there kind of in the sweet spot of these porous structure, and that kind of gives the uniqueness of these metal organic frameworks. So this is the main concentration of today's talk, the ZIF-8 or zeolitic imidaclylate framework. Let me break down the name for you. The zeolitic part comes from the shape of the structure. It has the same similar type structure to zeolite or sodalite if you want. So this is a cage structure which has a diameter in each cage of about 11 angstroms. And these cages are interconnected through a window of 3.4 angstroms. So these openings and this hollow cage structure actually allows material or gases inside the structure, and it can store within like a sponge. So that's the uniqueness of this ZIF-8. Another prominent character of this ZIF-8 is its linker rotation. So it can kind of swallow a bigger molecule by making the linkers rotate in a certain direction and make the opening a bit bigger. So this is one of the characteristics that I was actually investigating using adsorption, so that some of the materials or some of the gases that we introduced into the ZIF-8 actually kind of trigger this rotation of the ZIF-8, and the material actually went into the structure. So this is actually happening in not in a like a discrete way. It happens in a gradual change of angle, and it depends on the pressure of the gas. So that's the uniqueness of this ZIF-8, and that has been investigated for a long, kind of couple of years now. And there's been so many definitions to this rotation effect, and I will talk about a little bit that later. So that, and I want to show you some of the a real-time picture of an SEM image of this ZIF-8. It's a crystalline structure, so that you can see that's under microscope. It's something that is like a really real crystalline structure, almost close to the zeolite structure. Okay, so this one of these characteristics that I was talking about is the linker rotation property of this material. It has been investigated computationally as well as experimentally, mainly in the field of chemical engineering and chemistry. But I have introduced some of the statistical and thermodynamics into this equation so that we can understand it a bit more. So a little bit about the ZIF-8 properties is that, apart from this flexibility, it has a surface area of around 1300 meters squared per gram, which is quite a lot for a material in this size, or most of the materials that we find today. And this linker rotation is the other important part that we want to look for. So there have been so many evidences that this structure has been showing some flexibility in taking on some of the gases. So this is important because when we want to store gases inside the material or within the material, you need to have a higher capacity, or that can store gases inside in a low pressure conditions. So especially for methane or like a natural gas, that the gases that are basically in the energy field, especially those petroleum industry, we need a structure, or we need a material that can actually act like a sponge that can absorb gas and then release it on demand. So this is a great structure or great material that can be used in those applications. So that was the kind of a motivation that we had to investigate more onto this phenomenon. So there have been so many investigations have done before us, but we are doing it in a unique way that mainly we use our own theory, or like our own thermodynamics and statistical theories. So a little bit about this adsorption process, because it's it's not new to physics, but it's particularly new to the field of the dominant field of physics. But a material and an adsorption process starts with basically the chemistry, or chemists. They synthesize these materials in a lab on a bench, and it's a prototype material. And then it moves to move to our field, where we do the characterization. Some of the chemists also do the same thing, but we are using basically the thermodynamics and statistical physics to investigate this material using adsorption. So we are using isotherms with pressure to see the structural stability and how much material that can be adsorbed into this structure. And that's the part of the physicist or physics is concentrating on. And the next stage, so from the characterization, we can choose the best application for these materials, and probably some of them are going towards the device applications like solid state devices and electronic devices. And most of them are actually going towards the petroleum and fossil fuel industry, where the chemical engineers come to the play, where they start developing processes that can separate gases using these materials, and they check the reliability of this material and those kind of process development stage of these a big research area. So mainly the chemists, physicists, and material scientists are working on the prototype materials and up to the characterization of it. And then mainly the chemical engineers working on the process development and the characterization of the processes. So this is basically the big picture of the field of adsorption. So the techniques that we've been using to study these materials are actually, we call the adsorption isotherm. That's the primary data that we take from the system. So when the materials or when a material is introduced to a chamber of gas, as I showed you earlier, the material will trap the gas on just above its surface. So the materials that are on the surface is called the adsorbed phase, and the materials that are on the gas phase is called adsorbate. So at the point of thermodynamics, the chemical potential between the two layers, or between the two phases, needs to be equal, and that brings us a property that we can measure, which is the pressure from the adsorbed phase can be linked to the chemical potential of the adsorbed phase. So we use used the laws of thermodynamics and some of the statistical physics to figure out or actually develop these isotherms that actually shows the properties of the material. By just looking at the isotherm, we can actually kind of guess or give a good prediction how this material will actually perform under pressure and also with other gases. So mainly there are 7 types of isotherms. I don't want to go deeper into that part, but depending on the shape of the isotherm, we can kind of categorize certain materials into their certain classes. So this is basic setup that we are using to actually measure these isotherms. Most of the isotherms are actually done in a really low temperatures so that the other forces like the gases are kind of slowed down at that level so that we can see a clear interaction between the materials and the gases. So this experiment usually takes almost a month to completely take all the data we need, and it has to be kept on a certain temperature, like really low temperatures, like even low down to 30 Kelvin, to actually see the fundamental interactions between the material and the gases. So that's the uniqueness of our experiments, or that's where the physics comes in, where the chemists actually don't use this much of low temperatures, and then we can easily characterize the material or get most of the fundamental interactions. So we have done kind of 3 main projects or 3 main projects only on ZIF-8, and then we started introducing carbon monoxide, which is a dipole molecule, and see whether this rotation or this ZIF-8 is can absorb carbon monoxide, because that's another important application. And if it is absorbing this carbon monoxide, and how efficient is that? And we figured out that the carbon monoxide also triggered that rotation, so that because of the dipole interaction between the carbon monoxide and the linkers, so it rotates, and the carbon monoxide can be easily absorbed inside the material. So it's a good material to absorb carbon monoxide, which is a pollutant or a toxic gas, if you know. And another set of or another application or the field that that we were looking at is absorption of xenon. So this is mostly fundamental study, that xenon is the inert gas, and we want to actually basically study the structure itself. So we introduced a bigger molecule without any dipole or any other interaction. So xenon surprisingly opens up the structure again, because it is actually bigger than the opening window, but it actually went in to the structure. We will be able to see it in the isotherm with a jump in the isotherm, that it actually absorbed more into it. And this xenon was also shows us that the structure can be flexible to absorb a bigger molecules. And especially the xenon is another a particular application of xenon is where the nuclear power plant, there's a byproduct of nuclear, or rather they want to remove xenon and krypton from the nuclear power plants after a certain time. So ZIF-8 may be another option to absorb those radioactive atoms or radioactive byproducts from nuclear power plants. So again, this is more related to natural gas industry. We've looked into the methane and ZIF-8 interactions, and surprisingly, methane is also introducing, kind of a really change in the structure. It expands the structure, and the ZIF-8 absorb more methane into it. So this kind of shows us that ZIF-8 has so many applications, starting from capturing toxic gases like carbon monoxide and carbon dioxide, of course, and also absorbing the radioactive or rather inert gases like xenon in a different environment. And methane is another big application that, in the natural gas field, so that ZIF-8 was also another replacement to kind of capture methane or store methane and release methane on demand. So these options or these studies actually kind of gave us a good canvas to work with ZIF-8 so that it has so many different applications. So like the carbon nanotubes, I hope these metal organic frameworks will be the next hype in physics or next hype in the material science to work on these applications. So here are some of the applications that I've been, looking at, especially, characterizations of materials, especially in the gas sensing of electronics devices, mainly uses, these metal organic frameworks, especially ZIF-8, can be used to integrate into these sensors so that it will be more effective than the usual heavy metal gas sensors. And also mainly the industry is the pumping a driving force for these applications, especially the energy industry, the carbon dioxide capturing and the hydrocarbon separation, purification, especially in the petroleum industry. These MOFs have been using or tested upon, and they have been using it so far. And they're really effective, especially in the natural gas and hydrogen storage. And I can predict that it has a really bright future in this sector of energy, because we are now moving on towards like a storing hydrogen as fueling as a hydrogen as a fuel, and also some natural gas as fuels. So this kind of concludes my presentation today, and thank you for everybody to being here, and I will take any questions now.
Thank you, Dr. Dinuka. And now it's open for any queries. Dr. Dinuka, can I shoot a small question? This may be a dumb question, but it's very fascinating regarding your ZIF-8 research work. And also, may I know what gases would you recommend other than methane and this? You said xenon.
So our study,
other than that, what are the?
So I haven't included all the gases here, but we have done carbon monoxide and carbon dioxide together, and we also did some mixtures like methane and nitrogen, so to see how separation is coming in. So these gases are, we choose these three gases because of their unique properties. So anything that is having a dipole or like a strong dipole would be really interesting to see how the ZIF-8 interacts with them, and especially like the bigger molecules. Like we choose xenon, but we have also tested the krypton on it, and still it shows the same kind of effect. So we choose these three as a main kind of just to represent the three types of gases. Like the methane is mainly a hydrocarbon with it's slightly bigger structure than like atomic sized gases. But yeah, of course, I would recommend more like a carbon dioxide would be a good probing molecule for the ZIF-8. And also, I mean, of course, nitrogen was the one that they have tested first, and it has been done for a long time. Nitrogen was the kind of the gas which is used in absorption to mainly see the surface area of the structure. But apart from that, argon, hydrogen is also a good candidate, but we have to go for a really low temperature to actually see the fundamental interaction between the hydrogen and zephate. And that's quite hard to keep the temperature at a constant throughout the whole month. So hydrogen was a really tough in the sense of experimental techniques, but hydrogen would be a good candidate to test on zephate.
Okay, and also in the real scenario, we find these gases in a not in an individual manner, but as a
mixture,
mixed
right?
mixture of all these. Yeah. So is there any mechanism to track the amount of absorption that each and every molecule has incorporated to your material, zephate?
Yeah.
Is there any
a way,
mechanism for that?
Yeah,
to
there's a
distinguish
way
them?
So we can use the same fundamental experimental setup for adsorption, like volumetric adsorption, but we can kind of introduce a mass spectrometer and check, like we can basically see the partial pressures of each individual gas at the same time. And after equilibrium, we can test the partial pressures again. So there are a couple of different ways to test this mixtures. One is using a mass spectrometer and get the partial pressures.
Here's what I found from Wikipedia.
Oh, sorry. Partial pressures at the equilibrium. So the best way that we can do at our setups are basically using a mass spectrometer and use a mixture of gases. And at the end, we can see the composition after an equilibrium. So by looking at that and how many gas molecules or what the composition of the gas phase, we can predict how much is actually adsorbed in the structure. So that's just one way of doing it. There are two other ways of doing it. Basically, the chemical engineers do that. Still going to use the mass spectrometer, but they're using a flow of gas. So it's more dynamic system. So we are using a more static or a stationary system. So yeah, for mixtures, we have to use a mass spectrometer to identify the partial pressures and the composition of the gas phase.
Okay, thank you very much. And are there any questions from the audience?
Dr. Dinuka, it's a very nice presentation, and thank you very much. I have one question. You explain about the importance of MOPS for storing gas. So what is the function of MOPS? It reduces the pressure, or what is how we can use?
So I mean, as we know that most of the energy related gases are stored in high pressure containers, right? So in the you have seen it recently in Sri Lanka, like the explosions and the safety of that mechanism is not a good way to store energy related gas, like volatile gases. So zephate or most of the MOFs are kind of you can store gases in very low temperature, low pressures, because they can just select that gas and keep it at just above its surface. So it's almost act like a sponge. It's like when you put a sponge in the water, it absorbs the water, but it doesn't change. It just keeps the water inside its pores. And then when you do, like when you squeeze it, it just releases the water. But the same thing happens in the MOFs. You can, with a small bit of energy or like a energy chain, you can release the gas back. So the important thing is that we can store gases at low pressures, especially to fuels, like storing hydrogen in a container at a higher pressure is a safety concern. So we can store a much more amount of gas at the adsorbed phase. So it's an intermediate phase. It's not a liquid, but it's not a gas. So it's kind of trapped in the surface. So we can kind of store more amount of gas with less pressure with these MOFs. I hope that clear
Yeah,
this out.
I got understood. Thank you very much.
Okay, thanks.
Any other questions? So in the absence of any questions, let us conclude today's webinar. And it was Professor Dinuka H. Gallaba from the Department of Physics, Southern Illinois University, USA, and he was expressing all his knowledge on the title Versatile Supermaterial. So I would like to call upon Dr. Vasanthi De Silva to have the conclusion remarks.
Yeah, thank you, Dr. Chintaka.
Dr. Vasanthi.
Yeah, can you hear me?
Yes.
Yeah, yeah.
Hello. Yeah, okay.
Yes,
Okay,
we can
thank
hear
you. Yeah, thank you, Dr. Chintaka. So, I would like to thank our invited speaker, Professor Gallaba, so for your insightful and impressive webinar on CIF8, a versatile super material. So, also I am very happy to see you in this IPSL webinar platform as my friend. So I see you after a long time. It's very happy time for us. So definitely this is a good motivation to our undergraduates and the researchers to find out the new aspect of the material science. So it was very interesting to me. So the research work is collaborated with as a physicist and chemist as well as the chemical engineering. So our students can understand how they require the knowledge, fundamental knowledge to implement in the research work in their postgraduate studies. This is kind of a good motivation to them as well as us. So again, I would like to thank your time and your preparation on behalf of the IPSL webinar series. Also, I would like to thank our organizers from the IPSL committee for carrying on this continuous webinar series as a monthly event. Also, I would like to thank all the participants for this evening. Thank you very much on behalf of this IPSL. Again, I would like to thank our president, Professor Shanta Gamage, as well as our Vice President, Dr. Chintaka, as well as coordinating this event, Dr. Chathuri Nupearachi. Thank you very much all to have this great evening. Have a nice day to all.
Thank you.
Thank you.
So before we stop, I just want to thank everyone to be here, and especially Professor Shanta Gamage, who have invited me, and also Dr. Chathuri Nupearachi and Dr. Vasanthi De Silva to coordinating this event. And it's a great honor again to be in a part of this seminar series. Thank you.
Thank you very much, Dr.
Thank you. Thank you.
Thank you, Dr. Dinuka.